Ve şimdi de sunumlarını gerçekleştirmek üzere sahneye Sayın Uğur Yılmaz'ı davet ediyorum.
So, hello everyone. I'm Uğur Yılmaz, and I'm actually a senior quantum device design engineer at IQM, which is a company which basically designs quantum computer. And today I'm here to talk to you about the quantum supercomputer. So, this term might seems to be very fancy, but actually this is something that already exists. So, quick introduction about me and my company. So, as you can see, I did my PhD. I'm a doctor in superconducting physics, and I've always worked within this topic. And I think that the date of this conference falls very well in the sense that we recently have the Physics Nobel Prize 2025 with Martinez, Clark, and Devoret, which basically are initiating this field. So, quick numbers on IQM. So IQM is initially a Finnish company. So it was founded in 2018. So it's a Finnish startup first. And it then started to spread in several countries. So we have the headquarters naturally in Helsinki. And the second biggest office we have is in Germany, in Munich, where I'm coming from actually. We have over, as you can see, 50 nationalities. So there are other Turkish citizens like me in the company also working on the development of the quantum computers. For now, we are developing qubits up to 150 in numbers. And we also are providing a cloud service. So there is more than 2,000 users actually. We are about slightly more than 300 all over the world, because IQM has offices both in Asia and in US and in Europe. So almost half of the people in the company are PhDs. For now, we have investments up to 600, a bit slightly more than 600 million actually, and we have already built quantum computers, for more than 30 of them, and some of them were sold actually. So this is pretty much the products we are proposing. You can see there is this IQM Spark product, which is a 5-qubit product. It might sound very little, but the main goal of this product is to help education and researchers to get their hands on quantum computers. So this is basically a low-budget quantum computer that universities can buy. When I say low budget, we are on the range of 1 million. Then you have far more complex quantum computers with 20, 54, and 150 qubits that you can buy actually. And there is also this other services that we provide, which is the cloud service, and we call it IQM Resonance. And you can basically choose the machine you want. So there is this different topologies that you can see, crystal and star. This is basically just the architecture of the quantum processor that we're proposing. And so these quantum processors are about 20 to 54 qubits. And of course, this really helps everybody to get their hands on and to do quantum computation remotely and to probe the technology before deciding to finally maybe buy a quantum computer. So, I guess that none of you are kind of knowledge maybe in the field of quantum computer. You see some weird terms. I'm going to try to quickly explain you what is a quantum computer and why is it so interesting. So, on the market today, you have different types of quantum computer relying on different technologies. Here, the ones we are proposing, it's based on superconducting technology. So this is superconducting qubits, aka transmon qubits. You have different type of qubits. You have, for example, qubits which are based on the spintronic technology. You have qubits which are based on more optical side, photonic sides, which are basically ion trap qubits. But here, I'm going today, the product I'm presenting you is mostly superconducting technology. So what is a qubit? A qubit, actually, in analogy, you may all know the transistors, which are basically the basic foundation of CMOS technology. In the case of superconducting computers, what we are using is called a Josephson junction. So this is kind of simpler than a transistor. It only has 2 bounds. And this is basically what we call in physics a weak link. So what does it mean? It means that basically this component is on a superconducting state. And once you reach a certain level of current, magnetic field, or temperature, you're basically switching the components which is in the superconducting state to a kind of classical. It means that basically you have a component which is able to draw a lot of currents till it reaches limits and without any resistance. And over that limit, basically, you have resistance. So we are using the transmon in a purely superconducting regime. And what we need is basically what you can see here on the picture, a huge fridge. So we are engineering that transistor, which is called the Josephson junction, with everything around to match specific parameters. And we are cooling it down enough such that we can see those different quantization level, because what is just a superconducting loop with a Josephson junction? It's simply an oscillating harmonitor. So you basically are seeing those different energy levels on the, and you're able to basically tune precisely all those levels by engineering. And you need to cool down. And this fridge is basically cooling the chip at 10 millikelvin. To give you an idea, 10 millikelvin, it's minus 273 degrees Celsius. So this is basically the coldest point that you can find in the universe. This is this machine. Even in the sky, in the universe, you don't have anything which is colder than this cryostat, which is a dilution refrigerator. So you have those qubits, which are able to basically get into this very specific superposition state. You probably already have heard this name. And what makes the power of this quantum computers is the fact that you have the combination of the superposition state with the coherence, actually, that goes together. So I hope that you kind of roughly understand what a computer is. So as I told you, we have already sold quantum computers. And you can see that we've sold the quantum computers to also some HPC centers. And the latest one is Oak Ridge in US, basically, which bought a quite big machine. And you can see that we are among the top 10 vendors around the world, despite the fact that you might not have yet heard the name IQM. You can see that there are also quantum computers which are already set up in Asia, and hopefully soon in Turkey. So I was thinking of a way to bring you the quantum computers with data centers, but I mostly heard from the people before me that quantum computers is more like a threatening technology than something good. Actually, it can be used the way we want. So why am I talking to you about HPC center? First of all, they are basically always going together with a data center that is coupled to it. And also because we at IQM are the first company in the world to have properly coupled a quantum computer to an HPC center. And you can see that for any HPC center, you have 3 key points that are coming. So this is basically, first of all, to enable the research and innovation for all the scientists in the community, to help advancing the technology with new programs, new architectures. And this is probably one of the most critical points, very strategic and national role. So you have security, which is inside, of course, and scientific leadership. So scientific leadership is definitely making also the safety of a country and and raising the technology level of that country, which is quite critical. So those HPC centers, as we have heard from many people before me, they have one major problem. It's the energy consumption. It's going higher and higher and higher and higher because we are always in need of more and more and more data. And the computation power is also increasing, which means that the dissipation is also increasing despite this very smart architectures that we are using. So, of course, this objective of CO2 emission reduction is very important, but another aspect that many people do not consider is simply the fact that are we able to provide energy to those centers? Because if you need a nuclear plant just to power one HPC center, doesn't make sense. So what the quantum computer has to do with that is that a quantum computer, you all have to understand it, it's not replacing the classical way of computing. It's just a really novel way of computing. For example, using a quantum computer to do what we can do with a normal computer, this is probably the dumbest solution we have, because this is not made for this. Quantum computers opens you a very new perspectives in terms of computation, things that you're not able to reach with a classical computation. So, as we said, the current landscape of HPC, they are getting bigger and bigger in size, too expensive, and too high in energy and water consumption. Like I said, the quantum computer is able to do other types of computation, thanks to basically the superposition and the entanglement it enjoys by physics. And this computation is far more efficient than the classical way you have to do it. So basically, you are able, in very specific problems, to do a far more efficient computation. For example, I don't know, medicine development, cancer treatments, telecommunications. There are very specific problems. Designing, I don't know, some very specific components for spacecraft, for airplanes. You really have a lot of applications which are really case-specific, and it always needs to come with a classical computation. But the quantum computer can bring you definitive advantage on very specific problems that even classical supercomputers, in some cases, are not able to solve in a normal time frame. So as you can see here, I give you as an example what basically the National Energy Research Center on supercomputing is working on at the US. And all those problems that are basically here in yellow are problems that you can use quantum computer to enhance the calculation. So it's getting faster and faster, meaning less energy consumption, despite the fact that you need to have a fridge which is cooling the chip very low in temperature, which also has naturally, it's expand in energy, but it definitely brings you quite a bit of advantage. So why to combine quantum computer and supercomputer? As I told you, quantum computer is really strong at very high complexity for very specific problems, and we have low data. Low data means that you have, as your QPU, your quantum processor unit has not many qubits. The data that you're taking out, it's not that huge. Compared to, for example, the supercomputer, where we know that we are strongly parallelized, there are big data involved, and they are making really general purpose computation. And like I told you, the unique superpower of superposition and entanglement that you enjoy in quantum computer can make you really fasten some very specific simulations. So imagine that you hybridize those two solutions, so you basically have a tool which is able to optimize solutions for chemistry, for materials, and even quantum machine learning. So what is a quantum supercomputer? Like I told you, we already provided quantum computers to some huge HPC, which were installed. And here you see a rough schematics of what it does look like. So you have those 3 key elements. Like you can see, you have your supercomputer. And you have here your classical supercomputer. You have here your interface, which basically is a program to communicate with your quantum computer. So why do you need this interface? Because you need to kind of have a standardized protocol such that you can integrate your quantum computer to any of the HPC center. And what is needed to make those quantum supercomputers? So, as you can see, we have 3 big steps. Let's talk about the first one, the physical integration. What does it look like? So, here is an example. So, like I said, we were the first to couple. Here you can see that already in 2022, we coupled with VTT, which is the National Research Center in Finland. We coupled the first 5-qubit system with their supercomputer, LUMI. And so this was a work which was in conjunction with VTT. So IQM was strongly involved in the development of the QPU that is used here, together with VTT. And this is like really the first time that you have this hybrid service where you have a proper quantum computer which is communicating with a supercomputer. So this was just this is a way to open the field of this hybridization. And in 2024, what we did was far bigger because we put a quite bigger machine, which is now, I think, upgraded. So it was initially a 24-qubit system, if I remember well. And we now have probably a system which is probably a 50-qubit system. And this is at LRZ in Munich. This is this German supercomputing center. And we really have coupled our machine that you can see here. So you have here this white tank, which is basically the coverage of this fridge. And you have basically your quantum processor, which is here at the bottom. And all along, you have a lot of wires going on. So microwave wires, to be precise. So what did we do after all those coupling? So like we were the first one, we needed to define a way for any other quantum computing companies to kind of have a standardized interface to go together with a quantum computer. So here you can see that we have few of our colleagues at IQM which work together in close collaboration with LRZ. And we defined in a very technical way. So you have, I advise you to go read that publication because you have a lot of quite good data and concrete data about how to couple it and how everything is built. So, like I said, superconducting qubits have stricter facility requirements. They are more sensitive to the environment. But this can be managed, of course, with a careful site inspection. So basically, we go on site and we check the magnetic perturbation. We check the planarity of the surface, how stable the building is, because vibration, electromagnetic perturbation can basically influence the performance of the quantum computer. And here, as an example, like I told you, we have set up first at LRZ a 20-qubit machine, and we tested it for more than 150 days, coupled to an HPC in Germany. And actually, this came out very nice because you only needed a human touch once weekly to just fill up the nitrogen, actually, that you need to keep the chip cooled. Next, what is the second step of a quantum supercomputer? Of course, it is how to couple it with this existing infrastructure. So, basically, how does a quantum computer interact? How you can drive a quantum computer? You can see that here you have your terminal. So you are on your side building your own logic gates, your own circuits, quantum circuits, that you want to execute. Then there's this API that we developed, and you send it to this server. Basically, this server takes it, compile it, and basically handles also the queuing of the tasks. Then, once everything is ready, basically, the task at which has the highest priority, or which is the first to be handled, can be sent to the quantum computer. And then the quantum computer, basically, here you can see I didn't talk to you about those two big blocks. Those two big blocks, they are basically room temperature electronics, because the quantum computer requires microwave sources to be driven and read out. So what you're sending is very precise microwave tone to put exactly the qubit at the state you really want. And you also need a readout, which is microwave too. We are talking about frequencies between, depending on the design, it goes between 4 to 10, 12 gigahertz. So this range of frequency we are talking about. And yeah, basically, the quantum computer's room temperature electronic handles that, and then sends the raw results to this server that is basically then showing you what you obtain. So in HPC, there's a delicate palette of resources. We need non-blocking resource usage. So this is really HPC community and the way it works that puts those constraints. So we need also fair usage of those rare quantum resources. And you also need to be able to accurately handle the billing and the permissions. So any HPC center would require those 3 points. And there is this big point, which is we need to operate within the existing framework. So you cannot come in an HPC center and say, I want you to modify this interface, that interface, because the investment is on a different scale. So here is a paper that also I advise you to check. So here you really have the standardization of quantum computer access to HPC. So this paper is quite technical, and as you can see, you have your scheduler and your compiler infrastructure that works together with the HPC that is described, and you can are all peoples from Munich, actually, Munich researchers which are involved in this paper. And this workflow is actually very nicely described in this paper. The last step, what do you need? You need to provide the building blocks for this HPC. So how does it work? You have, I mean, in the company, we have defined 2 broad categories of how to interface a quantum computer with an HPC. Here you can see this, what we called iterative. So you have this closed system, and you have this very fast response between the quantum computer and the classical computer. So this is really, when you see that scheme, it's a very fast communication back and forth between the quantum computer and the classical system that you can even put actually inside the cooler. And then there is this second workflow, which makes more sense, and which is this sequential. So here you can see that you have a pre-processing, then you inject it to the quantum computer, you recover the data that comes out of the computer, and then those data that you have, which are mostly statistics actually that you get, you then post-process it. So one of the best way to do it for now, it's this way actually, this sequential way. And there is one thing that everybody needs to take into consideration, is that your quantum, you need to prepare your quantum state. So meaning that classically, you would need to tune with your HPC the exact shape of the signal that you're going to inject into the quantum computer, so into the qubits. But you need to take account one big problem. It's that your quantum computer, it is noisy. You are not at the absolute 0 degrees Celsius. Even though you're very, very close to it, it is still noisy. So, and this noise, not only is it linked to the temperature of the environment, but mostly it is linked to all those cablings that you bring from outside, and which basically brings noise to the system. And you have not only the magnetic perturbation, but also the thermal load that you're picking locally, which makes it work slightly different. And you can basically, with an HPC, help to prepare that. And of course, you can use those library those heavy library to help process the state of the qubits that you want. And then once you execute, you can do the post-processing. So this flow is very interesting because you can see here quantum error mitigation and quantum error correction. So before I heard about an intervenant here which said quantum computer is able to break encryptions, etc. True and false in the sense that the danger is there, of course. Quantum computer, very performant quantum computer is going to come, but it's not yet there because we are on this phase where we are in the era that we call this NISQ era, this noisy intermediate scale, because the computer himself is noisy. All the community right now is focusing on how to mitigate that noise such that you can make your qubits more and more reliable. So with what we call the fidelity, which is the measurement units of a qubit. So we need to basically increase the fidelity to a certain level, and then after a threshold, you're able to basically apply those techniques. So why is an HPC center required for that? Actually, the calibration of this quantum computer is very complex. We are using an AI program, which is basically scanning, and the more you multiply, you have to think that the system is physically tied one to each other, and that on the same chip or on the substrate, when you excite one qubit, you have magnetic perturbation that can disturb the other qubit, which is the neighbor or even further away. So you need to do some local compensation. You need to really calculate the whole electromagnetic perturbation of the chip such that you're able to get this very high fidelity level that you need for the results that you get to be valid, actually. So an HPC center is very, very, very nice in that aspect because you have a very strong computational power and you can do this quantum error mitigation and quantum error correction with it. With real systems that we installed, there were some are actually installed with HPC or with other partners collaborating for some very specific problems. We were able to put out here at least 3 application case. Here you can see that this was a collaboration which was done with Volkswagen, which needed our results on the solid state chemistry. And here another paper that I invite you to take a look on material science also. The behavior, simulating the behavior of the transition is also one way to use smartly the quantum computers. And like I said, we have installed our Radiance at Oak Ridge, so this national lab, so this HPC in US. And this, I think, it is under installation currently. Lastly, we very recently, less than a month ago, closed our B-Series funding, which was over $300 million. So actually, it was $320 million that we raised with a US investor, which basically helped us open the US market to sell our quantum computers. And you can see here our 2 CEOs, so co-CEO Miko and Jan. And here are basically the investors, the US investors. And this money basically will help us to improve our systems because, like I said, you're really struggling with physics. So the way you need to improve that is engineering. And this engineering has a cost. Those systems that we sell, the price might be expensive, but just the wiring cost inside the system, these microwave wires which are able to hold those temperatures, it's far from being cheap, and you need thousands of them. So in conclusions, we have built a quantum supercomputer, and you have seen that we can actually put them together with an HPC. The software framework which makes the integration already exists, and we also need to put more focus on those building blocks with HPC plus quantum computer workflow. And we really see a bright future because right now, the quantum computer by itself is not yet powerful enough to provide you extreme results. It's going to come soon. And here is the roadmap to help you understand when this quantum technology is going to be critical. So this is our roadmap at IQM. And you can see here that we are in the 2025. So we are right now going to release soon, hopefully for next year, this 150 qubit system. And you can see that what becomes dangerous, it's this logical qubit. So this is basically after you take your single qubit, you assemble them in a very smart way, and you make one logical qubit out of this assembly. And you have what we call this period of quantum utility, where you will see the quantum computer being really efficient in solving real-life problems. And then you have this critical period that we call quantum advantage, where when you are reaching those level of over 200 or 500 logical qubits, that's going to be quite critical for any classical encryption systems. Or, I mean, good luck for the future. In the meantime, I hope that everybody will cover themselves. And yeah, thank you. So if you have any question, of course, you can come to see me. There is the colleague Eric Mansfield, which is actually the one which prepared this presentation. And he is our product manager for HPC. So if you want to take his contact also, please feel free. Thank you.